This video provides a technical standard review of the Indian Roads Congress IRC Code IRC 6/2014, focusing on the standard specifications and code of practice for road bridges concerning loads and stresses. The primary purpose of this code is to establish a uniform and common procedure for bridge design across India. It provides standardized guidelines to ensure consistency in structural engineering practices. Professional responsibility is critical. Designing bridges requires qualified expertise and technical rigor. The code ensures work is entrusted only to qualified engineers with adequate experience, who remain the ultimate guarantors of safety. Bridge classification mandates systematic categorization based on design loadings. This national framework ensures engineers select appropriate parameters to match traffic demands and regional logistics, from minor culverts to major highways. The standard IRC loadings include Class 70R for modern heavy-duty traffic on high-capacity routes and Class AA for industrial zones and major logistics demands. Critical load combinations 202.3 define how dead load, live load, and environmental loads, wind or seismic, are combined. Engineers must tabulate these scenarios to ensure structures sustain the most critical forces under worst-case coexistences. Dead load encompasses the weight of all permanent structural and non-structural components. This includes the superstructure itself, as well as superimposed dead loads like wearing courses, railings, and utility ducts, acting vertically throughout the bridge's lifespan. The code provides standard material unit weights, such as reinforced concrete at 25.0 kilonewtons per cubic meter and structural steel at 78.5 kilonewtons per cubic meter. Standardized densities ensure all designers use consistent criteria when calculating permanent gravitational loads. Live loads are transient, dynamic weights of vehicles. Unlike dead loads, these are variable and must be placed strategically to induce peak stress. Design considerations include systematic vehicle positioning and worst-case analysis. Class 70R loading is the most severe condition for permanent highway bridges, accommodating modern heavy-duty traffic on high-capacity routes. It includes both 70-ton tracked and wheeled vehicle train configurations. Class AA loading is a specialized heavy-duty configuration for industrial zones and major ports, mandatory for critical national highways. It consists of tracked 40T or wheeled 35T vehicles, ensuring resilience against extreme industrial transport forces. General traffic loading includes Class A, the standard baseline for all permanent bridges, simulating typical mixed traffic. Class B is calibrated for lighter traffic on secondary rural routes or temporary structures, optimizing cost for low-intensity infrastructure. Multi-lane combinations vary depending on carriageway width. For wide decks, engineers must combine classes to identify the maximum cumulative stress scenario, for example, 70R in one lane and Class A in others. The congestion factor, 204.4, applies a 1.15x multiplied stress effect in locations like ports or industrial hubs where dense, slow-moving traffic is common. This preserves safety margins under extreme urban or industrial density. The lane reduction theory recognizes the low probability of all lanes being simultaneously occupied by the maximum design load. This allows for a 10% reduction for 3 lanes and a 20% reduction for 4 or more lanes, ensuring economic efficiency. Standard pedestrian live load is 400 kilograms per square meter, increasing to 500 kilograms per square meter for urban pilgrimage sites or fairgrounds. The structure must be checked for scenarios where footpaths are fully occupied, while the carriageway is empty, and vice versa. Curbs must withstand a local lateral force of 750 kilograms per meter applied at the top edge. Railings resist simultaneous horizontal and vertical forces, acting as a critical passenger safety secondary system. Crash barrier containment levels, from P1, normal, to P3, high, are selected based on the hazard level and design vehicle speed and weight. P3 ensures absolute containment for high-risk zones. Moving vehicles induce dynamic magnification due to road irregularities and vibrations. The impact factor increases static live load to account for these fluctuations, which is essential for long-term fatigue resistance. Impact percentage equations are span-sensitive. As span length increases, the impact percentage decreases. The material logic differentiates between reinforced concrete and steel bridges due to their distinct vibrational characteristics. The application in substructures recognizes that dynamic vibrations dissipate as loads travel deeper. Full impact is applied to the deck and bearings, linearly decreasing to zero impact at the foundation. Wind load analysis is mandatory, based on basic wind speed maps of India. It defines terrain categories to establish high-altitude wind pressure profiles for design. Transverse aerodynamics involve force acting perpendicular to the longitudinal axis. It is calculated using design pressure, projected area, and aerodynamic coefficients, including the gust factor and drag coefficient. Pier drag coefficients quantify wind flow resistance around substructure components. Streamlined shapes significantly reduce lateral loads on foundation. Longitudinal wind forces, acting along the bridge axis, are calculated as a percentage of transverse wind load. This is 25% for girder bridges and 50% for truss bridges. Hydraulic flow forces represent horizontal pressure exerted on submerged piers. This calculation ensures foundations remain stable during flood surges and prevents scouring-induced pier tilt. Forces on curves include radial thrust from vehicles on horizontal curves. Bearings and the substructure must resist this outward thrust to prevent shifting of the bridge deck. Buoyancy effects mandate that the effective weight of submerged members must be reduced based on Archimedes' principle. This is critical for ensuring the structure maintains effective gravitational stability during floods. Lateral earth pressure requires retaining structures like abutments to withstand active soil pressure. A live load surcharge accounts for vehicles moving near the abutment face to prevent overturning. Thermal movement considers two aspects: uniform expansion/contraction and curling due to the temperature gradient. This requires precisely designed expansion joints and bearings to prevent concrete deck cracking. Section 30 addresses seismic hazards. India is categorized into zones 2 to V, assigning zone factor Z to determine the effective peak ground acceleration required for structural design. Orthogonal ground shaking requires analyzing the structure for seismic forces in two horizontal directions and a vertical component. This ensures the design captures the worst-case interaction of complex seismic wave pulses on the structure. The design seismic force, $F_EQ$, relies on the inertial weight, which is the dead load plus a fraction, typically 20%, of the live load mass present during the earthquake. This represents the total inertial load the structure must resist. Bridge criticality, outlined in Table 8, uses importance factors. These factors specifically increase safety margins for lifeline structures, such as emergency routes, ensuring they remain operational post-disaster. Ductility and energy reduction factors are crucial. They allow for the design of lower forces by accounting for energy dissipation through the controlled, ductile deformation of structural members during seismic events. Anti-dislodgement systems are mandatory in zones I, V, and V. Seismic arresters limit deck displacement to prevent unseating and catastrophic collapse, ensuring the span remains physically connected to the pier, even if bearings fail. Navigation safety, 220, requires bridges over navigable channels to withstand accidental vessel collision. Design forces are determined based on the Inland Waterways classification. Impact energy calculation uses the barge displacement, $W$, and collision speed, $V$. This value directly influences the design of protective fenders or the structural robustness of the bridge pier foundation to absorb the massive strike force. Alpine and snow hazards, 221, are applicable in Himalayan regions, using a standard snow density of 500 kg per cubic meter. The design must account for the sustained weight of snowpacks to prevent excessive deflection. Pier collision robustness addresses horizontal impact, 222. Supports near the carriageway must withstand a horizontal collision force from heavy vehicles, ensuring a traffic accident does not lead to total structural failure of a support. The next scene presents image sources for the video, acknowledging the creators of the visual content. Continuing with the image sources, this scene credits additional third-party visuals used throughout the video. The final scene lists the remaining image sources, concluding the acknowledgement section.